aeronautical engineering, nuclear engineering. Those were the first of their type in the country were at MIT. In any case, Harvard between 1872 and 1917 tried to purchase MIT 3 times because they wanted an engineering school. People were building up engineering schools and whatnot. I handed out the little thing on leadership at MIT where I quoted Thomas Edison, where he says MIT was the greatest school in the country and blah, blah, blah. Because businesses were learning that engineers were useful to their professions or to their economy and stuff. So in any case, in 1917, actually between 1914 and 1917, MIT and Harvard merged for 3 years, and students were getting a degree from both schools in engineering. Professors had joint appointments at both schools, but in 1917, the Supreme Court of Massachusetts knocked apart the whole deal, and MIT was then forced to have to try to pay for these buildings you're sitting in right now. They had started building them. This building was built in 1917. And they had been building it, and they were trying to do the merger, and Harvard was going to pay for it. But all of a sudden, they weren't going to be able to merge because the Supreme Court of Massachusetts said that a private university couldn't buy the land-grant college. Okay? And so MIT was bankrupt because they weren't going to get some of the Harvard money. And an anonymous donor bailed them out with $6 million. Anybody know who the anonymous donor was? Building 6 is named after him. It's not Mr. Six, it's Mr. Eastman. George Eastman of Eastman Kodak gave MIT $6 million. Over his life, he gave about $30 million to MIT, which would be like $300 or $400 million today. Okay, he was very generous to MIT. He really liked MIT, just like Thomas Edison. Does anybody know what company Thomas Edison started? General Electric, right? So, in any case, in the meantime, Harvard didn't have an engineering school. So they took the land, Andrew Carnegie bought them, which was right across the river from Harvard Square, and they built their own engineering school. And today you can drive by it. It's known as the Harvard Business School. Because back then, businesses and engineering were sort of synonymous, okay? So the Harvard Business School is technically Harvard's engineering school, okay? But that wasn't why they came in 8th in the country in 1990s, okay, in engineering. Okay, questions people have? One question came up. One student emailed me, and he wanted to do his project on touchscreen displays. And of course, Wednesday's when you're supposed to tell me what your project is about. And you don't have to write up a whole thing. I mean, you can just scratch out in pencil on that little form I gave you what it is you want to do. I just want you to know that you thought about it. I wrote back that touchscreen displays, if you talk about the whole display, too complex, okay? It would be a superficial presentation to talk about the lighting and the LEDs and the stuff. If he wanted to talk about the coating on the touchscreen display, that would be fine. What's the coating? Anybody know? It's indium tin oxide. And what's unique about indium tin oxide? It's transparent. It's a transparent conductor. It conducts electricity and it's transparent, and usually those two things don't go together. In fact, it's the only material in the world that I know of that both conducts electricity, electrons, and is transparent. Ordinarily, if you have free electrons, it will absorb light, and therefore it's not transparent. It's the only material I know of. Okay, but there, I'm sure people. Well, I'm sure people are trying to develop other materials. Why? One's the wear resistance. No, it's not. When you're making touchscreens, there might be $1 worth of indium on there. Tin's not that expensive. Indium's about the price of silver. But the problem is it doesn't have great wear resistance. And people, you ever go into an automatic teller and down where they have the button in the same corner, and people hit it with their fingernail and it wears out? Okay, so wear is a problem. And so for example, if this particular student who will be making a presentation wants to talk about the wear resistance of indium tin oxide, he wants to talk about the properties of indium tin oxide and why it is both an electronic and an electronic conductor and transparent. If he wants to talk about how you process it, which is probably vapor deposition so far as I know, I'm not sure. Any one of those topics or a combination of a couple would be fine for a project. But you can't take something as complex as a display. You couldn't take something as complex as that projector, okay? Because what are you going to say in 10 minutes? Well, a projector projects light, okay? Well, I want something a little more depth than that, okay? So the reason I'm asking you to pick something, I want something very simple, because something very simple. Even a paper clip, if you get into it, there's problems of corrosion resistance, making it low cost, you know, design of a paper clip. How many designs of paper clips are there, right? Okay, you gotta make it out of steel or plastic or what, okay, and what are the trade-offs? I mean, you know, a very simple product will bring up lots and lots of questions, so I don't want you to come up with some complex product, okay? Everybody understand? Keep it simple. KISS, right? Okay, so that's my thoughts on the projects that you're supposed to talk about. So today, just to kind of review where we've talked about forming methods, and generally you can think of if you're going to use a temperature difference, which is what the blacksmith used to do, you have a cold tool and a hot workpiece. And so you can form it with the same material, but the tool is cold and the workpiece is hot, and therefore the workpiece deforms and the tool doesn't. It's not very useful if the tool and the workpiece have the same hardness. If I tried to deform clay with clay, what's going to happen? They're both going to deform, and I end up destroying my tool, right? So that's what the blacksmith did. There's also isothermal forming, which has been used for years, where you have a hard tool and a soft workpiece. Well, if I'm using a drill, I've got a hard tool, the drill, and the workpiece hopefully is not as hard as the drill. Okay? You can't drill diamond except with another diamond. You can drill diamond with diamond powder, but it's a very slow process. Okay? The tool is often heat treated. They learned how to heat treat steel back several thousand years ago. It really became an art about 1,000 years ago, where they used to, they didn't have a lot of steel. They had some steel. They got it from meteorites and other things. They could make it as wrought iron back 1,000 years ago, but they had to forge it, which is basically the top cold workpiece and a hot workpiece, a cold tool and a hot workpiece, and then they had to heat it and quench it and temper it. And one of the things, anybody know about the Damascus swords? The Damascus swords, they had nice little patterns on them that they etched on the surface. Anybody know they felt that the best swords were not just quenched in water, they were quenched in a slave, and not a dead slave, but a live slave. And that gave them power against the enemies to kill one of your slaves, to quench your sword. I'm glad I wasn't a slave back then. Anyway, so you anneal the workpiece, and there may be multiple anneals and multiple dies, and we've talked about different shaping dies and all the steps you have to go through, and you have to anneal in between. Not on every step do you have to anneal, but you can only get so much work into something before it becomes too hard and starts approaching the hardness of the tool. The other thing you can do is to use a die that has high hot strength and use something today that's super plastic, and we're going to talk about that. You can do everything essentially in a single die. Now, superplasticity, Backhoffen came up with, he reinvented it, rediscovered it, if you will, back in the early 60s. We've talked about it. I'm not going to talk, we're going to probably be tomorrow or so before we get to it, but let's see, oh, here it is. No wonder I can't find it. This is an example of a part. This was made in 1988, but in some of the superplasticity stuff, people were forming out of titanium superplastic parts by the mid-70s. That's one of the quickest adoptions of technology, less than 15 years, of any technology I can think of, okay? There's only a couple that I can think of. The average time to adopt a new technology in materials processing is about 20 years, okay? To do it in 10 or 12 years is incredible. Just demonstrates the need. But this basically shows, in the darkest gray here, is the final part, and I don't know specifically, but it's probably some part of aircraft part that has a bunch of ribs and is kind of an eggshell or egg crate type of construction. And so here's one of the ribs, stiffening ribs, and this is what they finally machine. The conventional forging would have been something in the white outline here, and the superplastically formed part would be something that would be in the gray part and the actual machine part. And if you go up here, conventional versus hot die, which means isothermal superplastic forming, the machine part weight is 28 kilograms. The formed weight for conventional was 154. That gives you a buy to fly ratio of about 6 to 1. Okay? Amount of machining was 126 kilograms. Well, if you're paying $300 a kilogram for titanium, you can multiply that out. This is not a cheap part. And if you can save 50 kilograms by going to isothermal forging at $300 a kilogram for your titanium, plus the machining cost, which probably brings it up to $600 a kilogram, you're saving a lot of money in the overall part. Okay, so the net savings of kilograms was 45 kilograms for that particular part. So there can be some big savings if you go to isothermal forging. Now, any questions on that? Today I want to start getting in a little more technical. A lot of my stuff's been kind of descriptive. I want to talk about plasticity. And this is actually in the very beginning of Hosford, first chapter. You have a stress tensor. This is a generalized stress tensor, and for plasticity, it doesn't matter what your orientation is. Sigma 1,1, sigma 2,2, sigma 3,3 are the tensile stresses or compressive stresses in the three directions. If they are actually principal stresses where the shear stresses go to 0, you can always find an orientation where the shear stresses can go to 0, then we just call it sigma 1 rather than sigma 1,1. Okay, that's the notation in the book most people use. So principal stresses are sigma 1, sigma 2, and sigma 3. Shear stresses, we have subscripts that are not equal or not the same, 1,1 or 2,2, 1,2, 1,3, and 2,3. And these three up here are the same, identical, as 2,1, 3,1, and 3,2, and you can prove that from symmetry and other things if you go to the whole stress tensor. But the important thing to remember is the three tensile stresses or compressive stresses, and if their principal stresses equal when summed together, actually I should divide by 3 there. That divided by 3 is the hydrostatic stress, and this is all in your book, okay? So the hydrostatic stress is 1/3 of the sum of those. Now, the strain tensor is essentially the same thing, except we write it down for strain, but the sum of the strains in plasticity is 0 because nu is equal to 1/2, and we're going to talk today about this R value, which is just the incremental strain in the 2 and 3 direction if I'm pulling in my 1 direction or compressing in my 1 direction. This is all in your book. That leads to, in biaxial straining, which is not something most of you have studied, but is critical to understanding deformation processing, particularly in sheet metal, very rarely are we processing something by just pulling on it in 1 direction. There is one example I can think of. We make millions of, well, no, millions of miles, millions of feet every year of something that we pull on in one direction. Can anybody think of it? Optical fibers. Very good. We take optical fibers, Corning takes optical fibers, they build up this composite layered glass, and then they just pull it. They just, without a die, they just pull it into long, thin fibers, and they put miles and miles and miles of that all around the country every year. Okay? That's because glass is Newtonian flow, which is not all that different than superplasticity. Okay? But we'll get to that a little bit later. But in general, if we're going to form something of more complex shape, it's going to be stressed in two directions if it's sheet metal. So we're interested in biaxial flow, biaxial plasticity, and we have, you've seen this before, we have either the Tresca condition, which is this kind of straight line yield criteria, and all we're doing is we're plotting sigma 1 versus sigma 3, or sigma 1 versus sigma 2. Usually the horizontal axis is our highest stress. If this is sigma 1, sigma 3, these would be principal stresses, but they don't have to be. It could be sigma 1, 1, sigma 3, 3. In any case, we have the Tresca condition. Does anybody remember? I think Dr. Belmar told you what the criteria for the Tresca condition is. It's called the MSC, maximum shear stress condition. So if you're talking about a non-crystalline material, the maximum shear stress would be on the 45-degree plane at an angle 45 degrees to your pulling direction, and the yield stress would be half of the pulling stress. That's P over 2 tau y, right? Or tau y would be the shear stress in the shear direction on the shear plane for a glass. That's not true of a crystalline material, and we're going to get to that hopefully today. The ellipse around this is the von Mises criteria, and the von Mises criteria is also known as the strain energy criteria. And the strain energy, maximum strain energy, there's only so much strain energy the material can support, and this is, see, the hexagonal prism is the maximum shear stress criteria. This is the general statement of the von Mises, and everything's a square of the strain, of the stress. That's a strain energy. A strain energy is proportional to sigma squared, okay? And so we have the differences between the three principal stresses happens to be 2 sigma y squared, so far as that goes. And that's the equation for the von Mises ellipse. Okay, there's the von Mises ellipse, and using that equation, sigma 1, sigma 2, you can come up with certain little criteria here. You don't have to worry about those things. They're I'm sure they're in the book somewhere. But in fact, that is just a two-dimensional plot of our three-dimensional sigma 1, sigma 3, sigma 2. This is a three-dimensional cube here, axes, and we have a cylinder going right straight up the 1, 1, 1 direction out of that cube, right? If you're a Miller indices materials person, okay? And all you're seeing is the ellipse is the cross section of a cylinder at some angle, and you have the Tresca condition, which actually is a pure hexagon if you think about it in the 1, 1, 1 direction, okay? So that's just sort of a review of things we've talked about. Now, it turns out today we're going to talk about the fact this doesn't have to be a cylinder. It can be an elliptical cylinder. Who says that the strength in the through thickness direction of a thin sheet is the same as it is in the sheet, pulling in the direction of the sheet? And who says that pulling in the one direction is the same as pulling in the two direction? If one is the rolling direction of a piece of sheet, and 2 is the transverse direction, and 3 is the through thickness direction, why would anyone think that all 3 of those have the same strength? particularly when you know that we get this grain structure, this texture that makes it look like the same type of structure as wood. Wood is clearly an anisotropic material, right? You can split it with a wedge if you split in the right direction. Anyone ever tried to split wood with a wedge in the transverse direction? It's not so easy, right?
Yeah. It'll split along the other direction.
Right. Because of Poisson's ratio, right? So next time you're splitting wood in the wrong direction, you say, forgot Poisson's ratio, right? And everybody will look at you a little funny. But anyway, okay, so it turns out to understand deformation processing, we have to get into biaxial straining and biaxial stresses, so far as that goes. So that's what we're going to talk about today. Now, one of the things that Hosford's got, and this is the old edition of Hosford, but he basically points out for plasticity, Hooke's law is stress is proportional to strain, and the proportionality is Young's modulus. This is Hooke's law, and strain to the 1.0 power is just the strain, so stress is proportional to strain with the you know, that you learn that as a sophomore in mechanics. But in plasticity, stress has a different constant of proportionality, and it has an exponent that's less than 1. And we know that because if you run a tensile test, and this says figure 3.3-4 in an old edition of Hosford. It's also in Backoff and comes from a paper in 1969 where they plotted true stress versus true strain on a log-log plot. And anyone knows that anything plotted on a log-log plot is a straight line. Well, almost anything. The straight lines could be different, but in fact for elasticity it's just 45-degree slope because Hooke's law, and Hooke goes back to the 1650s, okay? Stress is proportional to strain, and so it's a 45-degree slope, even on a log-log plot. This is elasticity, but when something goes plastic, even though we know that the stress-strain curve in a engineering stress-strain curve looks like that, and here's your, it's not true stress and true strain, but here's your curvature, and it turns out that if you put it on a log-log plot becomes a straight line, and it has a slope of n. Okay, now this is 1100 aluminum. 1100 aluminum is 99.9% aluminum. Okay, and the n value is a quarter that this person measured. Okay, so we have this relationship that we can use of sigma is equal to ke to the n, and n is going to be one of the important variables when we characterize different materials and how they're going to behave in different types of stress and strain. And in fact, if I go to typical sheet metal properties, let's see, aluminum alloys, this guy says, and this guy actually is the superplasticity book, but no, I'm sorry, this is Hosford. This is Hosford on page 289 of your edition, 3rd edition. So you don't have to copy this down, you just make a note if you want to know. It's on page 289. Aluminum alloys, instead of 0.25, he gives a range. Here's an R value. We're going to define that a little bit more and show you what it means. But R values can go from 0.6 all the way up to 5. And that's the strain in the 2 direction versus the 3 direction. Okay, that's what R is. It's that ratio. M is in fact M is if sigma is equal to K epsilon to the N. Sigma is also equal to, they usually use S epsilon dot to the M power, okay? And epsilon dot is just the strain rate, right? People always use epsilon dot, or use dot quite often for the derivative with respect to time. So this is just the stress proportional to strain. This is the stress proportional to the strain rate. a Newtonian material has an M of 1. It's not dependent on strain rate. It will just pull, you know, and will not neck down. It'll just pull forever. He doesn't have glass up here. Glass has a M value of like 0.8, and that's why Corning can take these optical fibers and just pull them for miles in tension without a die, because whatever shape it starts out with, you can just pull it forever and thin it down. You can pull for tens of thousands, if not hundreds of thousands of percent, and you'll end up with something. If it started out uniform cross-section, it'll end up a uniform cross-section. However, the M values for most materials are very low. They're very strong functions of the strain rate. If you can get M up to 0.3, it will start to behave superplastically. Okay? So that's the difference. Superplastic materials have large M values, like 0.3. Most metals have superplastic values on the order of 0.01 or 0.02 maybe. Okay? So most materials neck down. We'll talk about necking once I review it and try to remember how necking gets to be fairly complex. So I got to review it and get to that, but we'll get to it eventually. Okay. By the way, I haven't talked about schedule. I forgot to talk about schedule because I was telling the story of Harvard and MIT and engineering schools. The schedule is I'll lecture Monday and Wednesday this week, and Dr. Bellmeyer will do Tuesday, Thursday, and Friday. Okay? And right now we might even finish a week before spring break, but nonetheless, you can come and watch the other videos, which you haven't really watched a whole lot of. I think you've only done one as a class, right? Although the others are online, and you may decide that you're going to do those offline rather than making Jeremy come in and show it all to you. But we'll talk about that when we finally finish the lectures, the live lectures. And then sometime before spring break, after I get your things, your assignment on Wednesday of what it is you want to do a project on, I'm going to try to group things a little bit. You know, if one person is doing touchscreen displays, another person is doing something else on displays, or one person is going to be doing forging of titanium, and another one is going to do some titanium sheet metal part, I may try to combine things. So we'll do 2 a day. You're going to have about 10 to 12 minutes for your presentation. And then we're going to have 10 minutes of discussion, and so we'll be able to get about 2 in a day. Okay? And we'll do 6 or 7 of those. Probably won't start until like mid-April, but hopefully we'll finish by the end of April. Okay? So then you'll be done with the course. Ooh, and you can do all your exam studying for May. Lucky you. You know, I'm so glad I don't have to. When I left Bethlehem Steel, the thing that made me most happy was to no longer have to write a trip report. Whenever I travel for Bethlehem Steel, I'd have to come back and I'd have to write a trip report. Well, I went to Pittsburgh to see Westinghouse and met with, you know, blah, 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 blah. Anyway, I was so happy when I came back here as an assistant professor I didn't have to write trip reports. I was also very happy when I graduated from school and no longer had to take exams. Although, anyway, that's another story. There's still some types of exams you have to take. Now, this is the Tresca Criteria. If you just want to think of some little volume element with axes x1, x2, x3, uniaxial tension, the maximum shear stress, will be on some planes at 45 degrees. Now, this is assuming it's a non-crystalline material. It's something like clay. The maximum shear plane is going to be, without any crystalline preferred orientations from the crystal structure, it's just going to fail on the 45 degree plane in a direction that would be in the direction of these lines, and that's going to give you a shear stress on that plane, and things deform in shear, remember. That shear stress is going to be 1/2 of sigma y. Okay? The shear stress will be 1/2 of sigma y, and that's the basis of the construction of more circles, which I haven't gone through. But that's the Tresca criteria, and we've already talked about that. Now, well, actually I can put this up very briefly. This is out of your book, Hosford, when he's talking about plasticity. And this is just coming out in the 1-1-1 direction. There's the circle, there's the Tresca hexagon. The circle becomes an ellipse. That ellipse has interesting properties. And the ellipse is more physical, okay? Nature doesn't like corners, okay? Why would nature want to have sharp corners if you're pulling in a slightly different orientation? If you're pulling something in two directions, biaxial stretching, why would you have corners? But anyway, the ellipse itself has the property that the normal to the ellipse is the strain. So if I take, at this point, I actually am now in what we call a plane strain condition. If I make a vertical tangent here, then obviously the strain, and this strain will be d epsilon 1. There will be some vector of whatever the strain is in the one direction. There, if I did the other direction, there is no strain in the two direction. This particular position where I have a vertical tangency is called the plane strain condition, and it becomes very important in a lot of our processing. And the reason it's important is if you go back, and this is out of Backoffen, where he actually writes down Hooke's law, not like Hooke did. Hooke said stress is proportional to strain, but the modern version of Hooke's law says the strain in the x direction is 1 over Young's modulus times the stress in the x direction minus Poisson's ratio times the stresses in the other two directions. Okay, the sum of the stresses in the other two directions. So most people don't write this down, but if you're going to study plasticity, you need to start thinking about stresses and strains in multiple directions. I mean, everything you learned in mechanics before this was always sort of uniaxial tension or uniaxial compression. You got to start thinking about biaxial tension and compression. So Backoffen's got this little plot that for isotropic material, we got our von Mises ellipse. We would have plane strain right here, where there is no component in the two direction. Down here in uniaxial tension, where I'm just pulling a stress in the one direction, so this is just your tensile test, I'll have some strain in the one direction, I'll have some strain in the two direction. If it's plasticity, that is minus d epsilon 1 over 2, because Poisson's ratio is 1/2. Okay? So, and d epsilon total, the total strain, is going to be some vector down here. What is d epsilon 3 for uniaxial tension? If you remember, epsilon 1 plus epsilon 2 plus epsilon 3 is equal to 0. Okay, that's one of my criteria for plasticity. There is no volume change, and Poisson's ratio is 1/2. And so it turns out that d epsilon 3 is the same as d epsilon 2, and the sum of the three is 0. So if d epsilon 1 is positive, epsilon 1, d epsilon 2 is negative 1/2 of that, and d epsilon 3 is the same thing as d epsilon 2, and minus 1/2 plus 1 is equal to 0. Duh. Okay? Did that in my head. Didn't even have to do that in my calculator before coming to class. Now, down here, we have a condition where I'm compressing in biaxial compression. I'm compressing in, I'm sorry, this is biaxial tension. I'm sorry, this is balanced biaxial tension. I'm sorry, it's not balanced biaxial. It's tension in the one direction, and it's compression in the two directions. Sigma 1 is minus sigma 2, and I get a total strain vector like that, and I get d epsilon 1 is positive, d epsilon 2 is negative of that. What's d epsilon 3? It's 0, right? So this is also a plane strain condition. This is plane strain right here. This is plane strain right here when you have a 45-degree slope. Okay? And in fact, what is plane strain? You can produce a plane strain condition by loading a sheet, a wide sheet in a wide thin sheet in compression. So this is a plane strain compression test. Why is it 0 strain in one of the directions? Plane strain just means one of the strain components is 0. Either 1 or 2 or 3 has a 0 component. If I wrote down my strain tensor, one of these 3 is 0. That's what plane strain is. Okay? That doesn't mean that one of the stresses is 0, because in simple uniaxial tension, this stress is twice these two stresses, which are negative of that. Okay? All right, I'm sorry, they're Poisson's ratio times sigma 2,2 is minus nu sigma 1,1, and sigma 3,3 is minus nu sigma 1,1. None of those 3 are 0. In fact, the 3 of them add up to a hydrostatic stress. So when I pull a simple tensile test, I'm actually getting a triaxial component of that, because all 3 of them have some finite value. But if I'm talking a strain tensor, if any one of these 3 is 0, then I have a plane strain condition, and you can sort of see why a plane strain condition is something that I get sort of when I'm doing rolling. Okay? Big wide sheet. Why is it 0 in this direction? This is compression in this direction and compression in this direction, and no strain in the other direction, because this material out here is not yielding. If you want to think of it as after I've gotten a little bit of deformation in the center here, this material is still elastic. It's never deformed. The only thing that's deformed in here is the material in the groove, and it's lost thickness and it's gained width in the longitudinal direction. It has gained no width in the transverse direction. If no width gain in the transverse direction means the strain in the transverse direction is 0, this is plane strain. And this is equivalent, a balanced biaxial compression, not balanced biaxial, I mean a plane strain compression, which is sigma 3 compression and half of nu times sigma 3 for sigma 2. If I add a sigma hydrostatic component equal to sigma 3, I get balanced biaxial tension. Not balanced biaxial. I get a biaxial tension that's the same as this. So this is plane strain where I have sigma 1 is minus sigma 2. This is plane strain where I have sigma 1 is equal to minus sigma 3 over 2. Okay? So that's an equivalence of 2 plane strain conditions on that Tresca. And if you go around all the way around, you'll have 2 other conditions as well. So there's 4 conditions on the Tresca ellipse that are plane strain processing. And many of those occur in service. Okay? This is another drawing from Backhoff when he shows the equivalence between through thickness compression, if I add a hydrostatic component, is balanced biaxial tension. Where's balanced biaxial tension on this diagram? It's right up here. Okay? So a through thickness compression, which would be down here, is the same as that point up there for an isotropic material. Okay? You're looking askance. Okay? Let me show you again. A simple compression test, if I add a hydrostatic stresses to it will end up giving me balanced biaxial tension. Balanced biaxial tension on the von Mises ellipse is up here. Sigma 1, sigma 2 are equal. That's right here. And that's going to be the same as a simple compression test. Okay? These are not exactly intuitive. You have to play with them a little bit. But they are equivalent. So, if you will, this point and this point are equal, this point and this point are equal. And if I went around the whole thing, I would have other equal points on the other half of this. Okay? Just tension versus compression. So, now I've said it. You're supposed to believe it. You haven't challenged it. Anyone want to challenge me? No. Okay. Now let's talk a little bit about work hardening. And work hardening, basically, because I don't have something that comes up and is just perfectly plastic with no work hardening, I actually have some work hardening, which means there's some slope to the stress-strain curve. Basically, the von Mises ellipse just sort of grows. But who says that the ellipse is going to grow with the same amount of work hardening in the one direction as the two direction? The ellipse doesn't have to be just a larger version of the smaller ellipse. You can have a change in your major and minor axis if the material is not perfectly isotropic in the way it deforms. And in fact, we find that materials, real materials, are not isotropic. They actually can have ellipses that have large major axes versus minor axes, or they can have the opposite, and you can have positive or negative deviations from isotropy. It turns out that if I want to do sheet metal forming, I like to have long axis ellipses, things that are good in balanced biaxial tension, okay, that become stronger. Look at this. This material is strengthened by pulling it at the same time in the two direction. This is the yield strength for uniaxial. This is the yield strength for balanced biaxial. It's higher. It's stronger when I pull it in both directions. And if I'm going to do some deep drawing of cups, we're going to see that that becomes important. You can get better deep draws if you have an anisotropic stress-strain curve. And for the last 50 years, you've been able to buy steel and other metals based on an R value. And so, again, here's isotropy. Here's your plane strain value. If you have anisotropic, where the sigma 3 is greater than sigma y 1, 2, you actually are going to have plane strain at not a strain of a half, one of them being a half of the other, and being balanced. Your strain vector is still going to be perpendicular to that 1, 1, 1. Now, what was a cylinder, now it's an ellipse. And still, the strain vector can be proven to be perpendicular to that three-dimensional ellipse coming up in the 1, 1, 1 direction. But your strains in the different directions are different, and Poisson's ratio still has to average out to a half, but it's not the same in all directions. Poisson's ratio is not 1/2 in all directions. But they all have to work out, so there's no volume change. Okay? So I realize some of this is sort of counterintuitive. I'll give you an example later of why, maybe not later today. But what gives rise, why can we produce sheet metal that gives me non-isotropic behavior? And the reason is, mostly we're dealing with face center cubic or body center cubic metals. Aluminum and steel, 98% of all metal made, aluminum, steel, and copper. Together, those three are 98% of all metals made. And you only get to BCC if you start talking about zinc or magnesium or titanium. Anyway, these things are all in the noise. Not all titanium. Some titanium is BCC, if that's what you're thinking of, okay? But the alpha titanium at low temperature, pure titanium at room temperature, is hexagonal close packed, okay? But these materials tend to deform on the cubic materials, whether FCC or BCC, on the close packed plane in the close packed direction. It turns out FCC, which looks like one of these, ta-da, that's face-centered cubic crystal structure, and this is also face-centered cubic, just a little more complex, more atoms, okay? The white lines here are actually the face-centered cube, so you're just looking at a different orientation. But face-centered cubic, so there's the cube and there's the face center, okay? There's the cube and there's the center. What is the close packed plane? Or what's the close packed direction? That's easier, okay? In FCC, where do the atoms touch? Along here, right? In the 110 direction. Okay, so FCC has got a 110 direction, and the close packed plane turns out to be the 111 plane. The 111 plane is the one that goes, well, it's harder to see, but it's the one that goes, it goes from here, it's down, it contains two close packed directions. Actually, it claims three close packed directions. If you were to draw a that's the 111 plane, okay? And it's got three 110 directions. So I got an atom here, 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 okay? And they're all touching, okay, along these three lines. So that's FCC, is the 1-1 plane in a 1-1-0 direction, and body-centered cubic. Oh, by the way, this is aluminum. You can tell the atoms are gray. This is copper because you can tell the atoms are copper color. And it says that by the people who make these little models. Anyway, body-centered cubic looks like this. What's the close packed direction? It's 1-1-1 where they touch, all along the 1-1-1 direction, okay? And the close packed plane turns out to be the 1-1-0, okay? This plane is the same as this plane, is the same as this plane. There's an atom density of 1 on this plane, which is a quarter atom on each corner. 4 corners times a quarter is 1. Did that one in my head too. This plane, the 200 plane, is also 1 atom per plane, but there's only 1 atom, but it's completely enclosed by the 200 plane. 1 atom density per plane, 1 atom density per plane. That's the highest density plane. And so it turns out FCC and BCC are just sort of mirror images of each other in terms of what direction they want to deform. The easiest way for me to think about it is the direction in which the atoms are closest is the strongest direction, okay? And the fibers will align in the strongest direction. The crystals are going to rotate as I deform this polycrystalline sample, and I'll get a grain orientation, all other things being equal, and they're not all necessarily always equal, okay? But if I was doing wire drawing where they are all equal, I will get a texture with the close packed direction as the axis of my wire as I deform it. The crystals will rotate. So a wire, an FCC crystal that's drawn with lots of deformation will end up with a 1-1-0 texture in the axial direction, and a 1-1-1 texture for the BCC, and I'll prove that to you on Wednesday.